Equilibrium. All right. When we talk about chemical reactions, and we've talked about chemical reactions all year long, for the most part, you start off with reactants and you form products. Very good. Oh, Lord. And our arrow has looked like this. And it's been a one-directional arrow because we were saying, okay, we have our things that we start with and we're going to make our products. Done, boom, over with. Okay. The reality is the majority of the reactions that occur in the universe are not a reactant-formed product, but it's a reactant-formed product, and then the products turn around and make some reactants, or a lot of reactants. And this is to help conserve resources, conserve energy, things like that. And in your body, you have a lot of equilibrium reactions going on. If you didn't, you'd have to constantly be eating. I mean, 24/7, not just when you go to supper and just throw down a 20-pound steak or whatever. And there you go. So when we look at this generic equation here where we have sulfur dioxide reacting with oxygen to form sulfur trioxide, after some of that sulfur trioxide has been formed, it quickly reverts back and starts forming the things that created it. And it's kind of a neat little thing. So the thing that we're going to call this is a reversible reaction. In other words, reactants make products and then they turn around and start making the reactants again. And you'll notice that I have that double arrow here. And again, if you want to write it like I have it there, and I've gotten into the habit of just writing it like that, but if you're like, I like my arrows to have arrowheads, okay. Nobody's going to lose any sleep over that. It's just more effort. All right, so, I know, more efficiency. And here's an example. I'm not going to test you over all the molecules here, but you might see this in AP later on. Oh, happy days. Okay, now here is something that's kind of wacky. When we look at an equilibrium reaction, so here we've got, say, our reactants that we start with. How do we know that? Because we have something at the beginning, and then our products are down here. And then as time progresses, our concentration of the reactants decrease and our concentration of the products decrease until you get to this point right here in time. And it appears, if you were to watch this, it appears that the reaction actually stops. But it's very dynamic. In other words, these things are still being produced as time goes on. So as time's rolling on, the reaction's occurring. Now, one thing about equilibrium has the word equal in it. And the thing that makes it equal is not the concentrations or the pressures at equilibrium, but the rate. In other words, the rate in which the products form the reactants is equal to the rate in which the reactants form the products. So that's where equilibrium comes into place. And once that happens, then we're at equilibrium. And what's really cool as well, and this is a huge AP concept, equilibrium happens at the same time. In other words, it's not like, okay, O2 is going to get into equilibrium. Then here comes SO2. And then finally SO3. Nope. They all get into equilibrium at the same moment in time. Pretty wacky. Okay. Did you guys get that first blank? Good. Celeste, you got it? And here's another graph just representing the same reaction, except this time we're starting with the SO3 and then forming SO2 and O2. Okay. Also, these values can change with temperature. And we'll talk a lot more about that in AP, but I'm not going to talk about temperature as a variable for this class. Also, I mentioned that this is a very dynamic system. What does dynamic mean? What's that? Here, I'll give you. In other words, it's not a static system. What does static mean? Static doesn't move. Dynamic means it is moving. Good. So if you're going to become an architect one day, you don't want to design a building that moves. Okay, that's bad. We don't want walls moving. Doors, okay. Windows, okay. Walls, bad. Okay.
If you go to the bridge, sometimes you do In jail, you want your walls to be down there. You also want your windows to be down there.
Don't design a jail. All right, so this reaction is moving. Even though when you look at the graphical representation there, when you look at the graph, that it appears that it is actually stopped. Okay. All right, equilibrium position. All equilibrium position is telling us, and again, we're going to talk volumes about this in AP, and I don't think I told you how long we actually talk about equilibrium. It actually starts a little bit before fall break, and we continue talking about it well past Valentine's Day. Now, the thing is, you're like, we're going to talk about equilibrium that long? No, those are the type of reactions we're going to talk about. We're going to talk about acids and bases, salts, all kinds of things. But, again, the majority of the reactions are equilibrium type. In baby chem, we don't talk about it that much. All right, so let's see here. Equilibrium position, that's where I was at. So when we talk about equilibrium position, it's just where are these reactants at the point of equilibrium. And we're going to actually plug those values in here in a moment. And we can find out our equilibrium constant based on its position. Another thing that you might see, you won't see it in my questions, but you might see it next year, is that these double arrows don't have the same length. In other words, the longer the arrow is, the more that it favors, like A likes to form B, but B doesn't want to form A as much. But it does. There has to be something there for it to be at equilibrium. So if you see like really long arrows and a short arrow, then that means that A likes making B. We would call A strong, okay? Or it's definitely stronger than B for sure. Equilibrium constant. This is how your quiz is going to look. I'm going to be honest. Okay. So here is a generic equation where we have A plus B makes C and D. And these lowercase letters represent your coefficients. So the balanced equation. And the coefficients act like an exponent when you plug it into your expression there. The expression will always be one of the first things that you're going to write whenever working at any of these problems. So when we look at, and you don't have to have the EQ on there, but we always have products over reactants. And so you'll notice that the products are C and D, so I have C and D on top. And we can work in concentrations, or we can work in gases, and I'll talk more about this the next time we talk. And then you'll notice that your exponent, or your power, is whatever your coefficient says. And then the reactants are on the bottom. So products are always over reactants. And you'll hear me use that term, products over reactants. I have that in quotation marks. As I stated earlier, temperature does affect the reaction. It does affect equilibrium, but we're not going to talk about it in here. Okay? I just want you to know, and you'll see all my questions that I phrase it at a certain temperature, because you don't need to worry about what that temperature is. And here's a nice little representation showing that if I have dinitrogen tetraoxide making 2 moles of nitrogen dioxide, that when the temperature changes, so here I've got warm, here I've got cold, the reaction has shifted. And then when it's warm, we actually have more nitrogen dioxide than we do dinitrogen tetroxide. Okay, so it looks a little darker. And then as we form more and more of the dinitrogen tetroxide, it gets less brown, so to speak. Okay. The size of the equilibrium value, and when we do the calculations, this will make a little more sense. If the value is greater than 1, okay, greater than 1, what that means, if it's greater than 1, it favors the products being formed. Okay, now both are being formed, but it favors more of the products. If the value is less than 1, then it means once the reactants form the products, they immediately come back. But we still have some of the products. In other words, it doesn't really want to form products, but when it does, it reverts back. And then when the values are very close to 1, then we say that it's either way. Okay? There is no real favor, so to speak. Okay. And then expressing and doing some calculations. First one. Actually, in a lot of these problems, step 1 is really step 2. So step 1, write the equilibrium constant expression. But in a lot of these problems, I'm having you balance the equation first. So you got to have a balanced equation before you can write the expression. Then number 2, insert the concentration value or pressures. I'm not going to work with pressures with you guys, but concentrations And also, if it has a coefficient, raise that concentration to that power. And we're going to do some work with that. So let's look at the first one. Isn't that exciting? All right, here we go. Hopefully I got... Oh, good. All three of them are there. All right. So looking at the first question. Okay. Says the Haber process is a common reaction where ammonia gas, NH3, is produced from nitrogen gas and hydrogen gas. Calculate the K for this reaction at a certain temperature where the concentrations are given. Where nitrogen is 3.33 times 10 to the negative 3, hydrogen is 1.28 times 10 to the negative 2, and ammonia is 2.77 times 10 to the negative 1. So the first thing, since we don't have the balanced equation, let's write it. So again, it says where ammonia is produced, so we're going to put it over here. So ammonia looks like that. So that means we need to put our arrows there. Okay, so it's equilibrium, show a double arrow, or at least two arrows. And then we have nitrogen, it's produced from nitrogen gas and hydrogen gas. Good. So again, remember, if it ends in gen, it's diatomic. So we have our gens there, and it's all by itself. All right. Are we balanced? No, of course not. So what do we need to do? Put a 2 in front here. Can't move it. All right. So put a 2 there, and a who where? And then a what?
That's right.
We're good. Okay, good. Good back there, Bam Bam. All right. So now that we have our balanced equation, let's write our expression. So let me speed this up a little bit. So K is equal to products over reactants. So who's our product here? NH3. So I'll go NH3, put that in brackets. And it is, for the expression, it's in brackets because we're working with concentration. Remember that concentration is molarity, and that's how we represent it. But we do have a coefficient of 2, so square. And then we're going to put so we have products over reactants, so our reactants go on the bottom. So N2. And what coefficient does nitrogen have? A 1. So we don't, if you want to write the 1, that's fine, but I'm going to leave it empty there. And then H2, a coefficient of 3. Good. Okay. So write the expression first. Okay. And on the AP exam, you're always going to have to write the expression before you do anything with equilibrium. So, and that's an easy point. 1 out of 9. Boom, right there. Okay. That keeps you from getting a dash. How's that make you feel?
I like that.
That is good. All right, so let's do some plugging and chugging here. So ammonia, what is it? 2 point, so I'm going to go 0.277. Now, here's, even though I put molarity in the question for equilibrium, we don't show units. Now, about 5 years ago, we had to show units because we used to do an equation where we would convert the pressures into concentrations and vice versa. They have since removed that. So you don't have to show units on equilibrium. And I know that's like, oh, hallelujah, for a lot of you. All right, so since it's squared, make sure you square it. And then the nitrogen, we have it 3.33 times 10 to the negative 3. 3.33 times 10, I like those 3s. And what exponent should we have on that? 1, but so nothing. Okay. And then our hydrogen is 0.28 times 10 to the negative 2. And then we get to cube that bad boy up. Okay. So now let's make sure that we can type that in. Scoot you down a little bit. And let's see what we get first, and then we'll talk about how to type. So here's how to use the calculator, and I'm going to use the TI 30X2S. And this seems to be the most common calculator for a lot of us. But again, if you're using a Casio, you can easily use, instead of the EE button, the EXP, which is located right about here on your calculator near the bottom. So it's in this location here, and it sometimes has EXP or times 10 to the X. So that is what I'm talking about when I say EE, which is clearly marked right here. All right, so we have our expression written out, and we have the values input in, and it has, in some cases, it has an exponent. This one has a square, this one has a cube, but this one's all by itself. And I wrote out how to write it in on your calculator, or type it in on your calculator, but again, not all cases are you going to want to write that out, but make sure that we know how to type this in. So I'm going to take the top, which in this case is 0.277, and then square that. And then, since I'm dividing, hit the divided button. And the most important thing after you hit the divided button, make sure that you hit your parentheses. Okay? Because, again, order of operation is so essential here with the calculator. Now, I went ahead and set up a second set of parentheses. You don't necessarily need to if you type it in the way that I'm typing it in, but just to keep some of you from going crazy, it's not a bad idea. So 3.33, and then the EE is a second button, and then this one here. So notice it only appears as an E here. The EE is a designation on the actual calculator. And then to the negative third, not the minus sign, negative third. And I'm going to go ahead and close that parenthesis, and then hit times, open up another parenthesis. And again, the order of operation, I have two sets of parentheses that I started with. 1.28, again EE, so second that button, and the negative 2. And you could do a caret 3 here and it would understand what was going on, but I'm going to go ahead and close the parentheses, now use the caret, and then 3, then close the second set of parentheses, and I should get this value here, which is 1.09, actually 1.10 times 10 to the 7. So if you round it, 1.0 or 1.1 times 10 to the 7. Very good.
Hold on.
What?
Wait, is that a 2 or a 7?
That is a 7.
No, I'm not at the top. Is that a 2 or a 7?
That is a 2. That is a 2.
That's a 3.
All right, so here's how to type it in. Hang on. So 0.277. Hopefully you did the X squared button.
I got 1.09 times 10 to the 6.
I got 1.0987 times 10 to the 7. And then divided button. And I would open up two parentheses here. You don't have to if you do it the right way, but I'm showing two. 3.33 EE. And when you do the EE on the TI, you only do that one time. I've had people go second EE, so they see the EE in the calculator. To negative 3 times. Now notice I did double parentheses here. And then 1.28. 1.28 EE, negative 2, and then close that parenthesis, caret 3, close parentheses, equal. Okay? So if you type it in that way, the calculator really loves you. And it will give you, my calculator number is this, 87158. 5 times 10, or actually it says 07. Okay. Are you typing it in exactly? And using the negative, not the minus signs.
Yeah, I got it right, but I did it differently.
But yeah, it should just say one, there should only be one E on your screen. When you type in EE, there should only be one E.
I'm still come here.
And when I edit the video, I'm actually going to record me typing it in using this in a Casio. All right. Well, let's move on. All right, number 2. Let me scoot that down. Number 2 says sulfur trioxide gas is produced. Here, let's write that down. So sulfur trioxide is SO3, very good. Is produced when oxygen gas reacts with sulfur dioxide gas. Okay. So let's stop there. Is that balanced? Of course. So how could I balance that? Put a 3 in front of the O2. Put a 7. Okay, let me ask you this. No matter what values we put in front of the oxygen and sulfur dioxide, our oxygens are always going to be even. Okay, so we need to put, okay, so let's start there. And we can always erase. So we want to make sure that our oxygen on the right side is also even. So we have 2 there. All right, so how many total oxygens? 6. So I have 4 right now, but how many sulfur do I have?
2.
So let's experiment with a 2 there, and we're good. Okay. So don't overthink it. Just kind of rationalize it out. All right. So we've got our balanced equation. So let's write our expression. Okay, so what's the matter? I got you. All right. So what are we going to put on top?
SO3 squared.
Very good. So products. So SO3. And we will square it because there's a 2 there. And then on the bottom, what are we going to have?
O2 and SO2.
O2, and it is not squared, but it's just by itself, right? Bless you. And then SO2 is, that one is squared because we have the 2. Okay. And then from there, lug and choke. So let's see here. Our SO3 sulfur trioxide, there it is. So 7.44 times 10 to the negative 4. And that is squared. And the O2 is right here, so 4.19 times 10 to the negative 2. That one is not squared since there's no value there. The sulfur dioxide, 5.23 times 10 to the negative 3. And that one is squared. Let's make sure we can get that one. And I'll write out how to type that in. So 7.44 EE negative 4. Squared button divided by, and this time I'm only going to use one set of parentheses. So 4.19 EE negative 2 times 5.23 EE. And the EE button on your calculator or your EXP button or your times 10 or whatever button takes precedence over the times button. So it treats that like one, and it treats this like one entity, this like one entity, and then multiplies it together. So negative 3 and square button. Close it up. Wait for it. I don't remember the number. Anybody get a number? 0.483? That one does sound familiar. Yeah. Did you? Anybody else get 0.483?
Yeah, I got
0.4. You got 4.83 times 10 to the negative 1.
I got 4.89 times 10 to the negative 1. I think it might be because I rounded it.
How could you round?
Because for the 7.44 times 10 to the negative 4 squared, I rounded up.
You did not type that in again, did you? We'll take a look at it here in a minute.
No, once you say that,
In a minute.
right, once you say 4.8 times 10 to the negative 1 is close enough.
I hope so.
I did it right.
How do you get away with that?
Hold on. Hold on.
back.
You just. Oh, you squared the whole thing. Here, let's put that square on the inside. Come on, Celeste.
Well, it's on square, but it's like.
Well, do you see where my square is located at? Dang, you can't see it back there. Whose head?
You guys talk.
Name heads.
Everyone in this general area. Thank you.
Order of operation. All right, let's try the last one. Boys.
Give that back.
Thank you. All right, so number 3, the last example. A little bit different. This one I gave you the balanced equation. So it says the reaction above is at equilibrium at a certain temperature. Yes, it is. The concentration of the hydrogen gas is 3.0 times 10 to the negative 2, and the concentration of the hydrogen... Yours says iodine, doesn't it? Does it say iodine?
No,
Change it to iodine. Yep. Change it to iodine. Here, let's use a different color. My bad. Have that. So iodine gas. Look at it. Microsoft Word has had some serious, Word has
Yeah,
had
that doesn't
issues.
make any sense. You have the hydrogen. What is the hydrogen?
All right, so the iodine gas is 3.0 times 10 to the negative 2, and the concentration of the hydrogen iodine is 2.38 times 10 to the negative 1. Calculate the concentration of the hydrogen gas if the equilibrium constant expression has a value of 226.7. Kinda.
You have everything except one thing.
We do. So, first thing, what should you do? Write the expression. Very good. So, we need to write the expression. So, K is equal to what? HI squared. Very good. And then
Divided by H squared. Or no, just H. H2.
okay. And then the iodine. And this is 226.7. Okay. Now, we're looking for the iodine, right? So that means that we need to rearrange variables, multiply it on both sides, and then divide this on both sides. So now our expression, and you want to show this before you start going crazy with your calculator. Wait, what? We need the iodine by itself, so that means I need to multiply it on both sides. Yeah? I would love that, yes. And then we'll have our hydrogen and the 226.7. Okay? So once we have that, now plug and chug. We're finding iodine. I said that.
It said find hydrogen.
Yeah, I
What
made
hydrogen
it.
was.
Were you working ahead? Yeah, change that to iodine. Because I gave you hydrogen. Or no, you're right. I'm sorry. Yeah. My bad.
Wow.
You are correct.
Wow.
Go.
Yeah, I guarantee you Daryl went nuts on that one. Thank you. So that's how the expression should look. I know,
Your
I'm
work
sorry.
is not supported. You got it. Yeah, I would get you a dash.
All right, so at this point, plug in our values. So our HI is what? Where is it? Oh, 2 point. Here, let's move you over. There you go. That's good. I like that. So the hold on, Celeste. I'm still trying to plug and chug here. You're working way too fast for me. So 2 point. What's happening?
I was telling you what hydrogen iodide was, and you're like, hold on.
Oh, my bad. And then 3.0. 3.0 times 10 to the negative 2.
I got 4.3 times 10 to the negative. So I get this right.
Yeah? What would you get? Let's.
I got 8.38 times 10 to the negative. And it's not wrong.
How do you know this?
I got 4.3 times 10 to the second.
Let's see. Or I'm sorry, 8.33 times 10 negative 3?
Yep.
No, yeah, 8.38.
That's what I got.
8 my calculator says 8.32877 blah 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 blah.
Okay, then what?
Oh, yeah.
Can you come see what I did?
blah.
I got 4.3 times 10 to the second.
Finally, I got equilibrium. At 36.52, I got Yeah.
Well, it wouldn't have been as long.
Yeah.
Oh, I
All right, everybody good on that one? All right, so the homework is the ones. It's not up here on the board. You wanted to do more?